Now, we've always wondered how some people overeat and still don't put on weight. This question is about research related to such people. Um, People who don't put on weight, they spontaneously increase their non-exercise activity when they overeat, and that kind of explains why they don't put on weight. So the research suggests that non-exercise activity affects weight gain. So if non-exercise activity is increased, then the weight gain decreases. So the non-exercise activity can be taken as the explanatory variable, whereas the weight gain, which is affected by the non-exercise activity, is taken as the response variable. So we're trying to study the relationship between non-exercise activity and how it affects weight gain. So the first step to studying the relationship between two variables is to make a scatter plot. So we've used Crunchit to construct this scatter plot. The blue circles are the actual points from the data set. So for example, 135, when NEA is 135, the weight gain is 2.7, and this is the point that corresponds to NEA of 135 and a weight gain of 2.7 pounds. So notice that you see a red line in the scatter plot. That is called the estimate line or the regression line, or the least squares regression line. So it kind of estimates the overall pattern of behavior that can be seen based on the data that we collected. So if NEA is 135, the corresponding weight gain is about 2.7, and this comes from the actual data. So this is actual data or the real data, and according to this line, if I look at what the predicted value of the weight gain is, it would be a little over 3 pounds. So there is a difference between the actual value and the predicted value, because the regression line is just a model that estimates the relationship between x and y. And notice that none of the points that you see here in the scatter plot lie on the line. From the scatter plot, we see that the relationship between NEA and fat gain is negative, linear. By looking at the points, we can say it is moderately strong, but we cannot make a definite conclusion unless we know what the value of R is. So now that we know the relationship is linear, the next step would be to calculate R. Without knowing that the function is linear, calculating R makes no sense. So R tells us the strength of a linear relationship. So now that we know that the relationship between the two variables is negative linear, and knowing that it's linear is important before we figure out the value or the numerical value which gives us the strength of the linear relationship. So the numerical summary which gives us the strength of the linear relationship is the correlation R. And using Crunchit, we can see that the correlation is 0.7786. And just as we had observed from the graph, the relationship, the linear relationship, is moderately strong to strong. And these are the instructions for using Crunchit to find the regression line. We can also use a TI-83 or above calculator to find the regression line, and these are instructions for using the calculator. So either using Crunchit or the calculator, we can see that the equation that models the relationship between non-exercise activity and fat gain is given by this equation. So the intercept is the standalone number, whereas the slope is the number that's multiplied to x, which is the non-exercise activity. So we know what the slope is and the intercept is of the regression line. So here the question says, when NEA is 135, what is the observed or actual value of weight gain? So the observed or actual values come from the collected data, which is given in the form of a table at the beginning of the problem. So from that table, NEA, when it's 135, the fat in pounds is 2.7. So we have the regression line, and that is the point that falls just below the regression line, and that's the point that corresponds to these data. So that is the actual value. Now the predicted value always comes from the regression line. So we can plug in an NEA and find the weight gain. So let's see what the estimate or the regression line prediction gives us. We plug it in, and our calculations tell us that for an NEA of 135, the predicted weight gain is 3.04, which is slightly above the actual value, which is 2.7. Now these two values don't exactly have to be the same, because we've seen that the regression line does not have to pass through any of these points. It is just an estimate of the pattern which is formed when the actual data is plotted on the scatter plot. Now we can use the regression line to predict fat gain for a given NEA, but we also have to think about how good these predictions are. Now, how do we make that sort of conclusion? Because for any given data set, if you enter the numbers into your calculator, you're going to get a straight line, which is called the regression line. So how do we know that the predictions given by these regression lines are good? The number that tells us that the predictions are good is the numerical summary, which gives us the strength of the linear relationship. If the numerical summary, which is the correlation, suggests that the relationship is strong or moderately strong, then our predictions are pretty good. If the correlation was stronger, then of course our predictions would be closer to the actual values. So our predictions would be much better. The question says, what percent of the points can be explained by the regression line? By definition, the square of the correlation is the number that gives us the percent of the points that can be explained by the regression line. A percent can also be written as a fraction. So you can either express that as a fraction or a percent. So we take R, which is negative 0.7786, we square it, and that's approximately equal to 0.61. 0.61 is equal to 61 over 100, which is 61%. So about 60% of the points can be explained by the regression line. 60% is 60 over 100, which is 6 over 10, which is the same as 3 over 5. So 3/5 of the points can be explained by the regression line. Now the next question is, can you estimate the fat gain for NEA equals 1000? And we have to be careful here. We have the regression line, we can plug in a value of NEA and it'll predict a value of fat gain. But the estimate is valid only within the range of observed values. So in our question, the NEA ranges from negative 29 to 690, and those come from the observed values, and the regression line is calculated based on the values that come from the real world. So the regression line is good at it can be used for predicting values of fat gain given an NEA, but we can't just plug in any number into that equation. It would have to be within that range of values. Now let's see if 1000 is within this range, and clearly it is way out of range. So if it was close or within that range, we could have still used the regression equation. So this is important. If you're asked to estimate fat gain for an NEA that is far removed from the actual data, then the answer is well, it cannot be done because we don't have real world data to back up our regression line.